I am Professor M.V. Malkanawar, Department of Physics, Government First Grade Women's College, Jamkandi. Now, we have to discuss BSc First Sem, Second Chapter, Session 13, that is Elastic Collision in One Dimension in Laboratory and Center of Mass Frame of Reference. First, we have to see what is meant by elastic collision. What is meant by elastic collision? You know there are two types of collision, elastic collision and inelastic collision. In elastic collision, momentum and kinetic energy both are conserved. Characteristics of elastic collision: total momentum is conserved, total kinetic energy is conserved, force involved are conservative. Examples for elastic collision: collision between atoms and molecules, collision between microparticles and nucleus, collision between two smooth billiard balls. Now we see the elastic collision in the center of in the laboratory frame of reference. Let a particle of mass m1 moving with a velocity u1 collide a particle of mass m2 which is initially at rest in the laboratory frame of reference. After collision, particle m1 is moving with a velocity v1 making an angle theta 1 and m2 moving with a velocity beta 2 with an angle theta 2 with x-axis. Observe in the diagram both particles. One particle is at rest, that is of mass m2. Other particle of mass m1 is moving with a velocity u1. After collision, the two particles move in different directions as shown in the figure. Particle of mass m1 is moving with a velocity v1 making an angle theta 1 with x-axis. Particle of mass m2 moving with a velocity v2 making an angle theta 2 with x-axis. According to the law of conservation of momentum along x component, m1 u1 equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. Take it as equation 1. Then taking the component of momentum along y-axis. If you take the component of momentum along y-axis, before collision, particle of mass m1 is moving with a velocity u1 along x-axis. Therefore, y component of momentum is 0. After collision, the y component of momentum, if you consider, that is m1 v1 sin theta 1 plus m2 v2 sin theta 2, we get equation 2. According to the law of conservation of energy, half m1 u1 square, which is nothing but kinetic energy before collision. Total kinetic energy after collision 1 by 2 m1 v1 square plus 1 by 2 m2 v2 square. We get equation 3. If m1 equals to m2 equals to m, the angle between v1 and v2 becomes 90 degree after collision, because theta 1 plus theta 2 equals to 90. Theta 2 equals to 90 minus theta 1. Assume that m1 equals to m2 equals to m. Now equation 1 becomes v1 cos theta 1 plus v2 cos theta 2 equal to u1. That is u1 minus v1 cos theta 1 equals to v2 cos theta 2. Equation 4. From equation 2, v1 sin theta 1 minus v2 sin theta 2 equal to 0. Therefore, v1 sin theta 1 equals to v2 sin theta 2. Now, from equation 3, u1 square equals to v1 square plus v2 square. Therefore, u1 square minus v1 square equals to v2 square. Squaring equation 4 and 5. After squaring equation 4, we get u1 square plus v1 square cos square theta 1 minus 2u1 v1 cos theta 1 equal to v2 square cos square theta 2. After squaring equation 5, we get v1 square sin square theta 1 equals to v2 square sin square theta 2. Adding above two equations, we get u1 square plus v1 square minus 2u1 v1 cos theta 1 equals to v2 square. But according to equation 6, v2 square equals to u1 square minus v1 square. Therefore, u1 square plus v1 square minus 2u1 v1 cos theta 1 equals to, in place of v2 square, if you substitute u1 square minus v1 square, both side u1 square common, drop it, transfer minus v1 square this side, we get 2 v1 square, transfer minus 2u1 v1 cos theta 1 from left to right, therefore we get 2 v1 square equals to 2u1 v1 cos theta 1. If we drop 2 from both sides, v1 from both sides, then v1 equals to u1 cos theta 1. Take it as equation 7. Now, so if you substitute equation 7 in equation 6, u1 square minus u1 square cos square theta 1 equals to v2 square. v2 square equals to, take u1 square common, inside the bracket you get 1 minus cos square theta. v2 square equals to u1 square sin square theta 1. u1 square sin square theta 1. v2 equals to u1 sin theta 1. Take it as equation 8. Knowing initial values of m1, m2 and u1, we can find the final values v1, v2, theta 1 and theta 2 from equations 6, 7 and 8. From equations 6, 7 and 8. Observe here carefully. Knowing u1, u2, knowing m1, m2 and u1, we can calculate v1, v2, theta 1 and theta 2 from equations 6, 7 and 8. Now this is all about elastic collision in the laboratory frame. Now we have to discuss the elastic collision in the center of mass frame of reference. Go through the diagram. Consider a particle of mass m1 moving with a velocity e1 in the laboratory frame, and it suffers a perfectly elastic collision with a particle of mass m2 at rest, that is u2 equals to 0. The velocity of center of mass of a system of two particles related to the laboratory frame is given by Vcm, velocity of center of mass equals to m1 u1 plus m2 u2 plus m1 u1 plus m2 u2 divided by m1 plus m2. We are assuming that particle of mass m2 is at rest, therefore u2 equals to 0. Then Vcm equals to m1 u1 divided by m1 plus m2. This shows that Vcm and u1 have the same direction. Let u1 dash and u2 dash be the initial velocities of the particles m1 and m2 before collision in the center of mass frame. Then, according to Galilean transformation, observe here carefully, u1 dash and u2 dash be the initial velocities of the particle before collision in the center of mass frame. Then, according to Galilean transformation, u1 dash equals to u1 minus Vcm. u1 in place of Vcm, if you substitute m1 u1 and taking u1 common, you get 1 minus m1 by m1 plus m2. After simplification, we get m1 u1 by m1 plus m2, equation 1. That is, before collision, the velocity of the particle in the center of mass frame. Before collision, the velocity of the second particle m2 in the center of mass frame is u2 dash, u2 minus Vcm. u2 equals to 0, therefore you get minus VCM, that is minus m1 u1 divided by m1 plus m2. We get equation 2. Observe here carefully, u1 dash minus u2 dash equals to u1 minus u2. u1 dash minus u2 dash equals to u1 minus u2. That is relative velocity between the two particles in the laboratory frame and center of mass frame is same. u1 dash and u2 dash are the velocities of the two particles in the center of mass frame. u1 and u2 are the velocities of the particles in the laboratory frame. Therefore, relative velocity in both the frames is same. Let v1 dash and v2 dash be the final velocities of the particles of mass m1 and m2 after collision in the center of mass frame. Observe here, v1 dash and v2 dash are the velocities of the particles of masses m1 and m2 after collision in the center of mass frame. v1 dash equals to v1 minus vcm and v2 dash equals to v2 minus vcm, where v1 and v2 are the final velocities of m1 and m2 in the laboratory frame. In the center of mass frame, the center of mass is always at rest. Therefore, total linear momentum before and after collision is not conserved but is also equal to 0. In the center of mass frame, the center of mass is always at rest. Therefore, the total linear momentum before and after collision is not conserved but also equal to 0. That is m1 u1 dash plus m2 u2 dash equals to 0 and m1 v1 dash plus m2 v2 dash equals to 0. From the above relations, we get u1 dash equals to minus m2 by m1 into u2 dash and v1 dash equals to minus m2 by m1 into v2 dash. The negative sign indicates that u1 dash, u2 dash act along the same straight line in opposite directions. Similarly, v1 dash and v2 dash also act along the same straight line in opposite direction as shown in figure. Observe here in the figure, m1 dash, m2 dash, m1 dash is m2 and m1 moving exactly in opposite directions after collision, and in the center of mass frame before collision also they are moving in opposite direction but they are approaching, but after collision they are moving in opposite direction, they are not approaching, they are moving away from each other. Thus, we get, in other words, in the center of mass system, the two particles move towards each other before collision and away from each other after collision. This is all about inelastic collision in center of mass frame and laboratory frame. Thank you to one and all.